Okay, great.
Okay, good. Thanks, organizer, for inviting me to give this talk. So the title is Nuclear Tomography in UPC at RHIC. So we'll mainly go through detecting the charge radius and give you the final one is detecting the mass radius. But the last part, I think they're week 5, Daniel Brandenburg from the Ohio State will give you a lot more details.
Actually, you're not sharing the slides.
Yeah, slides is not sure.
You can keep going if you want.
Okay, so these are the references. Okay. And as I mentioned, the final state, there are only 2 tracks. It's either electron positrons or pi plus pi minus. There's nothing else. Okay. So okay, so 2-photon QED, you actually can read it from the particle data book. Okay, section 51.7, 2-photon processes. It will give you, if it's electron positron colliding, create 2 photons, which create E plus E minus. It will tell you the number of photon flux from 1 electron is this formula. Then all you need to do is take the flux from 1 electrons, another flux called N2 from positrons. You calculate the cross sections of photon into that process, and that's all you need to do. You get the cross sections. Okay, so you will think naively it's very easy natural extension to the heavy ions. You use the Wood section, and then the photon flux will be just the form factor Fourier transformation of this, and then this is the Q factors, and your cross section will be just these 2 form factors together. So if you have 2 ions which are identical, you have this F will be just 1 F. So that in that sense, if you measure cross section and PT distributions, you will be able to precisely measure the charge radius in these processes, because everything is QED. There's nothing else, right? Not even QCD, not even flow or anything. So you will think it should be really easy because the form factor is directly in there, right? So first, just some basics of the Bragg-Wheeler process. You have these 2 photons. The virtuality is really small, but in addition, because of the symmetry of the systems, the order virtualities actually cancel exactly in this process. And you create E plus E minus. To take the event, we not only measure the E plus E minus, we also factorize this, measure the forward neutrons, so that we know it's a collision, UPC collisions, and nothing else. So in our detector, the TPC, we make sure there are only 2 tracks in the system, E plus and E minus.
So, Zhang Bu, and this is good. This gamma star, those are not necessary to be there, right? But they could be there.
It could be there, so that you can actually excite it to the giant dipole resonance, and then you can actually take the event. In principle, we can also just trigger on the E plus E minus in the system, and that's what the CMS did, mu plus mu minus in the system, and there are only 2 tracks exactly muon to muons in the system.
But the purpose of drawing this dashed line there is saying that okay, they're independent, but you can use this to select a particular event class.
That's right. These 2 processes, because the excitation to giant dipole resonance, the time scale is very different, so you can actually factorize it.
So if it's not excited, you're not including those events.
In the particular analysis I show you, we can select on 1 neutron, 1 neutron, 1 neutron, 2 neutron, 2 neutrons. For 0 neutron, 0 neutrons, we didn't do it in the analysis I show you. But Atlas and CMS they did.
But does that actually cause some kind of imperparameter bias? Like,
Yes, I will show you. Okay, how that bias will do to you. So first, that we actually didn't analyze this part to start with. We actually analyzed because originally we want to see this electron and positron. We can calculate very precisely. We want to see if it's embedded in the QGP, what it will do. to be able to actually detect any magnetic field or this. So we actually didn't start with the ultra peripheral. We start with the peripheral, hoping to see any effect of the final state so that two electron positron pairs we can calculate precisely. So if any difference from the QED theory, which supposedly should be very precise, it will be the final state how the electron positron interact with the magnetic field, right? So in 2017, 2018, we measure the momentum distributions from uranium and gold and compare with the QED calculations I just showed you, and you see very big difference. And we were very excited, say, well, okay, if you compare with the model calculations, it's actually much broader. And one way of explaining it is say the electron positron pairs actually diffracted in the QGP magnetic field, and it seems the order magnetic field is about right. So that's very exciting. This is your product PT distributions, the gold, uranium, and the theory. So it's actually very different. It's get much broader. So in the PIL paper in 2018, we say, well, the theory actually failed to reproduce the PT distribution. That's clearly true. And one of the possibilities is these diffractions. By that time, we are already very suspicious because in the theory, the PT distribution is just random sample of the two photon flux. So it doesn't depend on impact parameter, doesn't depend on anything, which doesn't sound right if I have two ions which are far away. If you tell me the momentums of the interaction of the photons doesn't depend on where, how close they are, that doesn't make any sense to me, right? So we dig into the theory calculations. I mean, go all the way to 80s and 90s. So you can actually perform those other QED calculations. You can do this to find diagrams. You can write down all the formulas. If you expand to real calculation, it's actually more than 100 terms, but you can do that. And so the calculation we see actually is actually different. So we go back to the original, like the particle data book, where they make assumptions. So you can do, say, for two photons interactions to form vectors, but there's an impact parameter. You assume you integrate impact parameter from 0 to infinity, right? Therefore, E plus E minus is true, but for the ions, that clearly is incorrect. So from E plus E minus to heavy ions, if you continue with this integration from 0 to infinity, the impact parameter, you get back to exactly what I told you before, right? That's a very natural extension. But the problem clearly, they cannot be if we cannot put the ions on top of each other and call it UPC, right? So that actually makes a big difference. The other thing is the assumption that the PT distribution is just a random sample of these two photon flux and added randomly together. That clearly is also not true because all these factors actually depend on the impact parameter. You cannot permute, you cannot integrate the impact parameter first and then pretend the PT doesn't depend on it by using the uncertainty principle. So these are the two, I feel the two assumptions which are completely wrong that produce that theory results, right?
What are the two assumptions again?
So two assumptions. One is I can integrate impact parameter from 0 to infinity, and I can actually swap this integration the impact parameter 0 to infinity first to get these results. The other assumption is assume the photon transverse momentum is just due to uncertainty principles. I can randomly sample one photon with the other photon's PT and just numerically add them together because that PT depends on the impact parameter, right? So these are the two assumptions which are actually completely wrong in the heavy ions. Okay. So if we, yes,
You could imagine that you have a whole ladder diagram of electrons interacting with the Coulomb field. Why are they
yes.
so small?
So-
Why are they so small?
Okay, so this, there, I think in the 90s and 2000s, there are many papers arguing about the Coulomb corrections. The reason is we are measuring the leptons going out transversely. The passing time of the nuclei to each other is about 0.1 Fermi. So effectively, you don't have time to react to that. If we measure the same pair, but longitudinally, you will feel the Coulomb corrections. So all the kinematics are relevant. So for about 20 years, there are a lot of argument what are the Coulomb corrections. But if we integrate the cross section, then the Coulomb corrections is a big factor. But we are only measuring the 90 degree, which actually has small cross section compared with the total cross section. So the UPC impact parameter depends on what you are triggering on 1 neutron, 2 neutrons, or you actually triggering a nothing. You can actually compare their probability distribution as a function of impact parameter. And these are the model who will tell you what are the impact parameter probabilities are. But that has actually, I mean, some effect, but very small effect compared with the overall. I just told you those two issues, right? You can see their probability distribution are very different, but at the end, the PT distribution has some effect, but not that big. Okay, so we can actually use this calculation to compare with the total cross sections, with the polar angle distribution, with the PT distribution. Now, the QED calculation can have the impact parameter dependence, right? 60 to 80%, and the UPC. So you can clearly see the difference. The model can actually produce it very well. Compare with the original model, which just have no PT dependence, it's much safer at all PT because you are randomly adding two PTs together. Okay, so this is very good. So the model calculation actually can explain the data really well. Also at the LSC, also see one we didn't do. What they did is also only to check in the system, mu plus, mu minus, but now they also selecting the 4 neutrons to change the impact parameter. But the impact parameter is when these two nuclei actually never touch each other, and you can see also the momentum dependence. So it's clearly it's not a this dependence is not a final state. It's an initial state. The photon momentums are different depending on the impact parameters.
So the question is the star PRL in 2018 claiming the magnetic field effect. You're claiming that statement is not correct.
In the abstract, we didn't do that. We said fail to reproduce the PT distribution.
But in the interpretation, there's
In the interpretation, we give you examples that this could be the explanation, but at that time we didn't know what else.
but now we know it's not that's not the reason.
Now I think we know, but I will go to more details, right? So in the abstract, we know the model couldn't reproduce it. That's what we say in the abstract. But in the content, at that time we didn't know what's wrong with it. We give one possibility, say this may be able to explain it. Okay. And I think Presswitz already said, okay, we can also test by different using say, okay, is the dilepton yields and other yields scale with the G to the 4th power. This is the yields zirconium, rutheniums. But we also not only just that, we can also compare with other gold and uranium. That's a much bigger level arm, right? 40 to 90 G to the 4th power. That's more than an order of magnitude difference, and you can actually produce it very, very well. So now the picture is very clear. The photons, it's not due to a more transverse momentum distribution, it's not due to the uncertainty principle. It's actually permuted in space. They are at particular locations, you have particular momentum distribution. So it's like a Wigner functions, in the gluons or quarks, but it actually, the magnetic field or the photon field distributions has really a Wigner functions. It has the momentums and spaces are really correlated. Okay? So this is actually, for the first time, we actually can demonstrate that true. So you can actually map out the magnetic field distributions, right? And not only that, we can also say, okay, now we can use the R and skin depths and try to feed the data to see whether we can constrain both parameters, right? And these are one of the examples. You can say radius, skin depths, you scan the parameters, you feed the data to get a minimum chi-square. This, if you use the PP distribution from UPC, you will get these distributions, and you can convert into probability distribution functions of the electric field strength.
Does this mean the skin depth is most likely 0?
It means we don't have constraints on that
It's sort of
skin.
the same value of.
Yeah, like what was discussed yesterday. There's anti-correlations between A and R. Yes.
And so just to be clear, the radius here, because we don't have like baryon stopping, is this really the matter radius that you're dealing with, or what?
This, what we're discussing is the charge, because it's all QED process, right? So what this sensitive to is the charge radius. I will talk about the mass radius later. Okay, these are just charge radius, because all the process we see in here is two photons going into E plus, E minus, we measure E plus, E minus. So neutrons doesn't contribute to it at all. This process doesn't see neutrons.
So does this also work for PP collisions?
In principle, yes.
So you can measure the radius of the proton, charge radius.
For the charge radius of the protons in principle, but to trigger on the UPC, it's much harder in the protons. So,
But your final state is just a very simple E plus E minus or mu plus mu minus, right?
yeah, but you also need to take the accretions. Right? Okay, so let me move on. So we can actually compile all the data together now with all this with the process, the skin depths and charge radius. For the UPC, we can actually constrain it very well. But there's anti-correlation between R and A. This close point is from the low energy charge radius measurement, so you can see it's very consistent. For the peripherals, it seems to be symmetrically bigger. If you say, okay, I don't have any final state effect, I just measure the radius, it seems to be a little bigger, like 2 to 3 sigma bigger. So we have to see if more data will be able to actually see whether it's final state or initial state. By the way, we also changed the NN cross sections to see whether it depends on what cross section, nucleon cross section we put in, whether 1N, 1N, and XN, XN. If we calculate the RMS of the radius, you can see the error bar is actually quite small. Instead of this band, if you calculate the RMS, they are actually collapsed into a much narrower distributions. One of the features I told you is this divergence. For example, for infinity gamma or E plus, E minus, you will have the infrared divergence. But for heavy ions, because it's regulated by gamma square and by the form factor, it's actually there is never a divergence. There is no infrared divergence, or it's the high energy divergence. For example, for E plus, E minus, you have to cut off at the high Q square. Also, you have to cut off at the very low Q square. Otherwise, it actually diverge, right? The Coulomb field diverge. But for the heavy ions, it actually automatically regulated at the infrared regulated by gamma factor, which is no big, and a high energy is actually automatically cut off by the form factor because it's big, right? And we can actually test this by studying the energy dependence. The mean PT at low energy, it actually gets bigger because the projection of the electric components outer Lorentz boost on the longitudinal direction is actually bigger. That's why it's very weird distributions. At low energy, your PT distribution actually get a bit higher. And we actually can test this with low energy data. Okay, thank you. The other one, we can also see, for example, if you have field fluctuations, it will give you a higher side tail, right? And with enough statistics, you will be able to try to test this because it will give you higher energy photons. Most precise test is at LHC. They didn't calculate the PTE, but they calculate this alpha angle because their momentum is very high. They can measure the angle, diffractive angle, much better. And recently, Atlas published this paper, and they asked us to make the calculation and compare with data. They didn't tell us what the data is until it actually appeared in the archive. So the black points are the data, and the red point are using the photon Wigner functions. Assume they are real photon Wigner function formula in the system. The blue dots are the QED calculation I just told you. Those are all the QED calculations, and you probably cannot tell which one with which one because they agree so well, right? The only difference, tiny differences, almost at angle 0. There is tiny differences, and this may be due to the final state magnetic field. We will have to see, right? Just to zoom in so that you can see, right? Again, if you cannot tell because they agree so well, and we actually didn't know what the answer is. We just, Atlas asked us to do the calculations, and they never tell us what the results until we see it in the archive. So what's the next step is, I told you all of these calculations, charge radius, but that's not actually our goal. I just try to convince you we actually know what we are doing. The calculation is very good. So the main thing is you going to more central and see whether there's deviations, whether there's due to final state magnetic field effect. And this will be, I feel, will be the holy grail of measuring whether the QGP has like conductivities can trap magnetic field. And this will be one of the way you can actually measure it, right? So in the last few minutes, I will tell you measuring the mass radius by using the polarized photons, which I convince you the photons are polarized. We can actually measure the distributions. Now it's interact with gluon to create vector mesons, and that it's not, it doesn't depend on charge, it only depends on gluon. So this process actually can measure the mass radius. The paper was published in Science Advances last month. So there are you need three ingredients. One is the photons are linear polarized, so that we actually know the orientation of the vector mesons. There are actually two wave functions. One, because an ion can emit photons, interact with permanents on the other ion, but it also can do the other way. So you actually have two vector meson wave functions, not two vector mesons. They are at a very far distance. So then they actually have interference. And this interference, at the end, we only see one vector mesons. It's all wave functions interferes. And we measure the vector meson became to pi plus pi minus. So at the end, we only see one pair of pi plus pi minus, but it comes from two vector meson wave functions, okay? And so we know it's vector meson because the emitted mass looks like a rho. And we know it's polarized because we can actually measure the decay angle relative to the parent. And the polarization, the cosine 2 phi is actually 40%, so it's a huge effect. So we know all this. And also the key distribution, this is very small, right? 50 MeV. Okay. And just to make sure we are on the same page, it's two wave functions. At the end, we only detect one pair of pi plus pi minus. So these are not two row zeros, two row zero wave functions. Somehow it creates two wave functions, has interference, give you pi plus pi minus. We also measure the orientations. Okay. So it has been possible before, say if you measure the T distributions from the vector mesons, the measure slope is the extracted radius is too big. And the reason is because in the past, this effect has never been taken into account. So this interference actually makes the radius too big because it's blur the whole thing. Okay. And you can see if we take different orientations, the results are different. So for gold, this clearly cannot be, you are measuring the size, right? Because it actually, your nuclear size depends on the decay orientations. So after we understand this is an interference effect, we take that into account, we can actually realistically extract the radius, right? And these are the radius we extracted. And with this radius, because it also takes away the photon momentums, because the interference and directions also exactly the same as the photon momentum direction. So you not only take out the interference effect, but also take out any photon momentum in the transverse plane, which contribute to blurring the whole system. Okay, so these are the table we get from calculating the radius. And also in the 70s, there are measurements from the electron scattering at high energy as well. Okay. And you can actually compare this with the previous publication about the neutron skin. The goal here, okay, probably it's not very clear. The goal here is actually quite consistent with the previous measurement, but the uranium, somehow it's very big. We are not sure whether this is actually real, maybe it's due to the deformations, but if that's true, maybe some clever theories can figure out why it's this. And in some sense, then we will be able to use this to measure the deformations, right? But the best way will be the lab, which if we run that, then we will be able to test whether that's true, right? Because that is not deformed. And if we get a different answer, that will tell us. Right?
Sorry, what were the 3 points?
Yeah, 3 points, what are they?
So this is the goal we measure with 0.17. Oh, yeah. Okay. Neutron skin from this method, 0.17 from gold, 0.44 from uranium.
Yeah.
The other one is the PREX measurement.
Or go.
Which one is which?
No, for lead.
You did not measure the lead.
We did not measure the lead. This will be what the PREX give you where it is 0.28, right? Our measurement of the gold is 0.17. Our measurement of uranium is 0.44. We're outside this plot, right? Just to make sure.
But then what is that? Do you have one for that middle one you say is for lead, but that's not your data?
That's not our data. So we are arguing, has been arguing we should run that for 2 weeks a week, then we will answer that question. Whether that is somewhere here or it's here, and then may be able to calibrate whether the deformations cause this difference.
So
right?
your y-axis is the skin, right?
Yes. And this part is actually from this publication.
So I think that to me, there are two motivations, right? Very nice. Is first of all, it's a different method and the good is consistent. And then you wonder if you can provide measurement for lead. That may be
Okay.
useful.
And one more slide, then we finish, then we come back to the question.
Sure.
How about that? Because, so now I told you the interference, you need this wave function go this way, this wave function go this way, and they are two wave function interfere, they never actually collapse, right? So one of the interesting question is, if I add a noise to the system, if I move to peripheral, do you still see this interference? Or by adding the quantum noise, you actually destroy the interference. And we actually make that test. In the peripheral, your cosine 2 phi distribution and interference still there. So that means even you added noise into the system, the wave function actually never collapses, the interference going on. Okay, that's actually quite interesting as well. So Daniel will give you talking about a lot of other fancy measurement we can do, but this is just give you one of the examples. Okay, and of course you can do same thing at jet side. The law decay immediately, so two wave functions are 20 Fermi apart. The law is only that time is only 1 Fermi. So the interference actually passed to the daughters. The wave function never collapses, and that wave daughters interfere. Jet side is very different because jet side decay lifetime is much longer. So if there's interference, it has to be the jet side itself interfere. So there are many things we can test as well. Right? This is one of the prediction. With one of the assumption, I actually think this assumption is incorrect. So, but we can discuss it if you have any question about that. So in summary and perspective, we now understand what happened with the QED process in the UPC, in the breadwinner processes, and it can become a very precise tool to measure charge radius, measure mass radius, but also testing the final state, whether the QGP has magnetic field. And this is actually quite exciting. There are also many quantum wave function entanglement we can test in the future. And I just gave you one of the examples. Okay, thank you.
Very much. Very nice. Let's go Jackie first.
Yeah, so I'm curious, do you know what the Q squared and X are roughly? Because I'd imagine those are quite different than what you get from CREX 2.
So for the photon energy, it's about 80 GeV. For the Q squared, it's almost the photon Q squared is almost 0. So you can effectively make the Q squared equal 0 photon energies of 80 GeV, roughly.
Is it related to this?
Otherwise, yeah, go ahead.
Otherwise, we have several. Yeah, let's go with Bjorn first. Then.
So if you go back to the plot of his skin thicknesses of the whole world data there. So
It's not really a plot, I just pick 3 points there.
no, but regarding the plot, there is a uranium-238. Is that the other data? Are those 2 points experiment on the very right in the actual plot? Are those data on uranium skin thickness, or what is that?
Yeah, I think these are the data, right? These are the predictions from equation, from
But
calculation.
I thought there was no other data.
I think this is what TH,
Okay, so this is a
uranium is like here.
would be there.
Would be there.
I see. Okay.
Way in.
I'll go back to slide 28. So, yeah, so, yeah, I didn't understand. I was suggesting like the two daughters from the same row, that their wave function are independent from each other after the decay.
No, after the decay, the two daughters, they are entangled,
They must be
but they have a fixed phase. That's very important. And that's all you need to make the interference. Yes. So these two wave functions, their phase can be random. If they don't decay, these two wave functions, they won't give you any interference. But as long as the decay daughters has a fixed phase, you will always produce an interference. Even these two low wave functions are random, has a random phase.
I didn't understand what you mean by interference between the daughters.
So-
interference must happen between the wave function of rows. Each two daughters, they still entangled, right? They organize
Two daughters are entangled, right?
the other also entangled.
The others are also entangled. That means their wave function has a fixed phase. Okay, that's unique. Then these two wave function pi plus, they at the end they have to produce one particle, right? Pi plus. There's only one particle exists. These two are actually just wave functions. So at the end, they produce a pi plus six. Their phase are in sync. You produce a real particle there. That means pi minus, their phase are in sync because they have a fixed phase. And that's where you produce a pair which has this cosine 2-phi distributions. Okay. At the end, there is only a pair, pi plus, pi minus. There are no two pairs. So this interference is actually at the wave function level. Okay. If they cancel out, then you don't see any particle at all, right? So at the end, there is only one pair, one pi plus, one pi minus, but they all come from two wave functions.
I'm just, very interesting discussion about here. I just want to get back to the measurement.
Yeah.
So the main measurement that you got for the neutron skin was that you measured 2 electrons, is that right?
No, the neutron skin is through the vector mesons because otherwise the
Oh, you measured 2 pi.
2 times.
What are the energies of those pi?
So the Q, okay, so let's go back to this. The PT of the law is very small, so you can ignore it.
Mhm.
So the pion momentum is just the law decay into 2 particles. So the law,
Okay.
the law is 700 MeV, so it's 300 MeV each roughly. So roughly 300
You
MeV.
just took a look for 2 electron tracks to the star.
To pi plus,
Pi,
pi minus.
yeah,
We
pi, yeah.
exactly, that's what we did exclusively, only 2 particles in TPC. For the charge radial measurement, it's only pi E plus E minus in the TPC, nothing else. We specifically said nothing else in the system.
What was the momentum of the electron?
Okay, so let's go to the mass distribution. Since the PT of the parent is almost 0, right? The embedded mass is from 500 MeV to 2 GeV, so you divide by 2,
Oh,
right? Because the parent momentum is very small, right? It's only 20 MeV.
thanks.
So it's effectively just half of that.
Okay, can you go to, actually, just 2 quick questions, so. Slide 33. Double slit experiment with a screen you put in between. So are you saying, I mean, if you have a solid screen, then you should not have an interference, right? But if you have a partially, so you're going to modify, I mean, what's your expected signal?
From originally, I expected the interference to completely disappear, but clearly it's not, right? And so if you ask my expectation, I was expecting this UPC, then it gone down to 0 if you add any noise.
Oh, I see.
Okay, because now all the remember the definition of coherent is the final state and initial state, and the ions are the same. This all everything break up. You even create a lot of particles. These are number of particles in PVC. You still see the interference. You can argue that, well, if it's a solid or it's a, I don't know how to define that, right? Clearly, if it's a pions going through the system, it will impact, but it seems it didn't do anything at all. It's a wave function, so maybe. So if we go to more central, we will maybe be able to see it, but we will see.
You think that you can check the central. There will be possibility.
We need to take more data. You can see the error bars already getting big. Right?
Okay, slide 13, just click. the this sigma B, that's the part that you extracted from the feed, right?
Yes.
I mean, this is also different between gold and uranium. Why they different in the two systems? This is something to do with the low meson, the size of low meson, right?
No, this is depending on their modulations, depending on their impact parameters, right? And so it's more or less, I feel it's more related to the average impact parameters.
No, but the fact you need to apply this sigma B correction, that's because of you have some hadronic part,
No.
no?
This is because this oscillation.
Yeah, but you need to find the minimum. You can
That's
only use the minimum to determine the radius. So therefore, this sigma B is controlling how much this is modulated.
Yeah, but these modulations, there are only two particles in the system. It has nothing to do with ionic.
But why the uranium has smaller, much smaller modulation? Uranium.
Yeah, that's one of the questions. Maybe it's because of the deformation, but it also related to how far they are, right? If it's very far, then you probably don't have the modulation will be weaker. Right.
How about this sigma value will be in the Osborne equation? What would you expect? Will be even bigger?
I don't know. You need to calculate it, right? Also, I mean, just to remind you, we are only fitting the first slope, right? There are actually peaks which will tell you the detailed distribution. We didn't even touch it yet, right? So these are actually very important. Just to be clear, all we tell you, we are just fitting the first diffracted peak. We haven't even tried to see second and what happened, how they should be able to tell you the detailed structure distributions, and we haven't even touched it. So any theory who can maybe develop the models to fit it, you will be able to extract the details of the distribution, because the higher T, you actually are more sensitive to the detailed structures of the nuclear. Now, what I just tell you is more like a overall snapshot of the overall distribution, right? Because we are only fitting to the first slope.
Okay, so there's several more questions, but we're kind of out of time. So I think maybe we should cycle back after the last talk for discussion. If you want, you can add them to the Google Doc. It would help to remember the discussion. But for now, let's think.
But also week 5, Daniel Brandenburg is going to discuss with a seminar so that you guys can ask any questions.
You are not here.
Thanks again.